Before discussing about the reconciliation, we see what is the order and the degree of a recurrence relation. Just it is a Fibonacci recurrence relation. Fn is equal to Fn minus 1 plus Fn minus 2. N is greater than equal to 2 or greater than equal to 3. This recurrence relation, every recurrence relation almost they have order and the degree. Now discuss about the what is order and what is the degree of a recurrence relation. Then we shall bifurcate them as a homogeneous and the non-homogeneous. Then we will try to solve them on the basis of the given theorems. Now first, what is the order of a recurrence relation? Let us say here f of n is a recurrence relation. Say it is f of a1, a2, a3 or so on up to f of an minus k. Then n is equal to k is the order of recurrence relation. In practical problem we can find it very easily. Let us see, here is the Fibonacci recurrence relation. Here n minus 1 and n minus 2. We see n minus k, tell me this, put n minus 2 is equal to 0, then n is equal to 2. N is equal to 2, it gives the order. It gives the order of the recurrence relation. Or we take some another example, say f of n minus 7 times fn minus 1 plus 3 times fn minus 2 minus 4 times fn minus 3 is equal to 0. It is also recurrence relation. Here we see in the sequence n minus 1, n minus 2, n minus 3. It is the oldest sequence or the latest. Put n minus 3 is equal to 0. Then we find n is equal to 3. It is the order of a recurrence relation. So always remember the least term in the recurrence relation, if we put it equal to 0, that gives the order of a recurrence relation. So every recurrence relation have the order? No. It may or may not be. We shall discuss the examples after that. First of all, we will see what is the order and the degree. Now this is the order, and now we will see what is the degree of a recurrence relation. Here we keep the same examples and we shall discuss what is the degree of a recurrence relation. Let us remove all this. If we consider this example of the recurrence relation, first we will have to convert into the characteristic equation. That is a characteristic equation. Characteristic equation, it is an equation converted from recurrence relation to the algebraic equation. How to convert it? Let us consider some variables, say r. You can consider any other also. No, I consider here, say any variable r. We start them with r. Here value of n is equal to 3. Value of n is equal to 3. For this term n is equal to 3, we write r raised to the power 3 minus 7 into, for this r raised to the power 3 minus 1 and minus 1 plus 3 times r raised to the power, here n values 3 minus 2 minus 4 times r raised to the power 3 minus 3 is equal to 0. Again concentrate. Let us consider any variable, say r. Let us consider any variable, say r. You can take another one. No, we start with number 3. It is the order of the recurrence relation. Here n is equal to 3. Put 3 on the power of the r. Then next member is n minus 1. N minus 1 means 3 minus 1. Next member n minus 2. 3 minus 2. Next member n minus 3. It means 3 minus 3. No. Reduce it into the algebraical equation. R cube minus 7r square plus 3r minus 4 is equal to 0. R is to the power 0, 1. No, it is called the characteristic equation of a recurrence relation. It is necessary when we deal with the recurrence relations, we first of all convert the recurrence relations into the characteristic equation and then we solve. With solutions we will see them later on. That is the order and the degree of a recurrence relation. If we see this Fibonacci number, the recurrence relation, here we can write it in the form fn minus 1 plus fn minus 2 is equal to 0. Here n is equal to 2. It is the order. It is the order. In this example, we can say the degree is the power of the highest term, that is 3. Degree is 3. Now we see this example, fn, we consider a variable r. N is equal to 2. We start with, here n is equal to 2, but we put it in the power r raised to the power 2 minus r raised to the power 2 minus 1 plus r raised to the power 2 minus 2 is equal to 0, that is r square minus r plus 1 is equal to 0. It is the characteristic equation. It means before finding the degree of a recurrence relation, it is necessary to convert the recurrence relation into the characteristic equation. Now what is the degree of this equation? Now degree is 2. Order, its order 2. These are the two main basic things. And remember one thing, the degree and order here we see in the example seems to be same, but it may or may not be. Degree and order, the both examples we have taken, they appears to be same, but they may or may not be. We will discuss them later on. No, degree and the order. No, we will bifurcate these recurrence relation into parts, that is homogeneous and non-homogeneous parts. First we see what is the homogeneous and the non-homogeneous. Homogeneous recurrence relations are those relations which do not have any term, which is dependent upon n. So, let us take two examples simultaneously. Here there are homogeneous and non-homogeneous. What is the difference between both the recurrence relations? I say homogeneous means there should be no term depending upon n. For example, say that is fn minus 2 minus 7 times fn minus 1 plus 4 times fn minus 2 is equal to 0. This recurrence relation does not depend any value of n. Don't count this n. This n gives the order and the degree. Let us say we convert first of all it into a characteristic equation. Here order, we see order is put n minus 2 is equal to 0, then n is equal to 2. Now we write the characteristic equation of this, that is r square minus 7r plus 4 is equal to 0. Here its degree is equal to 2. Now see, we have no term in this characteristic equation which depend upon n, because each term we have transferred on the right hand side. On the other hand, if we see this example, fn minus 7 times fn minus 1 plus 4 times fn minus 2 is equal to 2 plus n into 3 raised to the power n. Now, this term on the right hand side cannot be transferred on the left hand side because it is not the member of the homogeneous part. Now, it is the non-homogeneous equation. How? This part we see again the same, r square minus 7r plus 4 is equal to 0. Again order 2, degree 2. But it is not homogeneous, it is non-homogeneous. It is non-homogeneous. Why? Because this term cannot be transferred to the left hand side. As we change the value of n, this term will keep on changing and changing and changing. So such type of the relations, they are reconciliation, they are create the non-homogeneous reconciliation and they are the homogeneous reconciliations. Remember, in the both cases, we can find out the characteristic equation, their order and the degree. But the difference is only between their solutions. They have different pattern, they follow the different theorems, and such relations, they follow the different theorems. First of all, we will discuss about the homogeneous reconciliations, then we will see non-homogeneous. First of all, see for few more examples of the homogeneous and the non-homogeneous. Let us say it is an minus 5 times an minus 1 minus 6 times an minus 2 plus 7 times an minus 3 is equal to 0. We can use a or f in the reconciliation. Here we put n minus 3 is equal to 0. This implies n is equal to 3. It is the order. Then convert it into the characteristic equation. We start with n is equal to 3. From here, consider any variable r. R raised to the power 3 minus 5 into r raised to the power 3 minus 1 minus 6 r raised to the power 3 minus 2 plus 7 into r raised to the power 3 minus 3 is equal to 0. It is r cube minus 5 r square minus 6r plus 7 is equal to 0. It has degree 3 and it is homogeneous. How we can say it is homogeneous? Because there is no term present in this reconciliation which depend upon n. We have transferred each and every term on the left hand side. No. Again we see another example of non-homogeneous. Say an is equal to n times an minus 2 plus 2 raised to the power n. It is a given reconciliation. So we have to find out its order, degree, and to check what is its nature, either homogeneous or non-homogeneous. Say an, put n minus 2 is equal to 0. It means n is equal to 2, it is the order. Now we write the characteristic equation. For characteristic equation, we write it an minus n times an minus 2 is equal to 0. We cannot transfer this term on the left hand side because it is not the member of the recurrence relation. It's only a constant with the variable n. As the value of n we changes, its value changes every time. But if any reconciliation which contains such terms which depend upon n, they are non-homogeneous. from non-homogeneous, we always separate the homogeneous part. That is the terms which can be transferred on the left hand side. We cannot transfer it on the left hand side. No, it's is r square minus n into r is equal to 0. Here n minus 2 is equal to 0. We write order 2 degree the largest power of the variable, and it is non-homogeneous. It is non-homogeneous. Why it is non-homogeneous? Because due to presence of this term. It depends upon n. As we changes the n, its value changes. But if you think, when we change this n, why we don't change this n? What is the recurrence relation? Recurrence relation, every term of the recurrence relation, you see, it is itself a sequence. Just say 1 plus 1 is equal to 2. 2 plus 1 is equal to 3. 2 plus 3 is equal to 5. It is the Fibonacci numbers. But it is not a Fibonacci number or the term. That it makes any sequence recurrence relation as a non-homogeneous. Let us see four more examples. First of all, it is very necessary to identify the given recurrence relation is either homogeneous or non-homogeneous. Secondly, to find its order and degree before we start solving them. Let us see another example. Say an minus 4 times an minus 1 plus 4 times an minus 2 is equal to n plus 1 into 2 raised to the power n. Now it's very simple to identify. This term cannot be transferred on the left hand side because, let us discuss about this recurrence relation. At the first look, we can identify it is non-homogeneous because it is the term which makes it non-homogeneous, because this term depends upon n and it cannot be the part of any recurrence relation. That first of all we identify it is non-homogeneous, then we separate the homogeneous parts. Homogeneous part is an minus 4 times an minus 1 plus 4 times of an minus 2 is equal to 0. Now we can write order. It is 2 of put n minus 2 is equal to 0. 4 degree, convert it into the characteristic equation. Order 2, n is 2. We take the variable r square minus 4r plus 4 is equal to 0. And its degree is 2. These are the three main characteristics of a recurrence relation. To identify it is non-homogeneous, its order and its degree. So let us take another example. Say an is equal to under root of an minus 1 plus a square n minus 2. Let us check it. Either it is homogeneous or non-homogeneous. From here we can simply find out n minus 2 is equal to 0, n is equal to 2. It is the order of the recurrence relation. Now we can write it r square is equal to under root r plus an minus 2 means square means plus 1, or we see n is equal to 0, that is plus 1. Rather it seems to be some complicated, but we see r square under root r and 1. There is no term which depend upon n. It is a homogeneous. So we conclude it is a homogeneous part. Then it has order. We know it is order is 2. What's about degree now? Degree here we cannot define. We write cannot be defined, because this term is in the square root and we cannot solve this equation under the given theorems of the recurrence relation. We cannot define the degree here. It does not mean it does not have any degree. It may have, we can find the degree in some other topics of the mathematics, but in this recurrence relation we cannot define the degree of this. Similarly, we get some other examples, say an is equal to a square n minus 1 plus an minus 2, an minus 3, an minus 4. Here is the given recurrence relation. We have to identify either it is homogeneous or non-homogeneous. First of all, we see the smallest number here is n minus 4 is equal to 0. It means n is equal to 4. It is the order of this recurrence relation. Now, first we convert it into the characteristic equation. Here, r raised to the power 4 is equal to r cube whole square. We write in this way. This square is for this term. And n minus 1, 4 minus 1 is equal to 3. Plus an minus 2. An minus 2 means r raised to the power 4 minus 2 into r raised to the power 4 minus 3 into r raised to the power 4 minus 4. That is r raised to the power 4 is equal to r raised to the power 6 plus r raised to the power 3 into r into 1. That is r raised to the power 4 is equal to r raised to the power 6 plus r raised to the power 4. We say there is no term present in it which depend upon n. So we conclude it is homogeneous. It is homogeneous and of order 4. Here 2, 1, it is R3. Now what's about its degree? Now see, r cube into r is equal to r cube into r cube plus r. We cancel this, then r is equal to r cube plus r. Now here degree is 3. Degree is 3. If there is the common terms on the both sides, we can delete them or we can cancel them, and the final power of the variable gives the degree of the recurrence relation. So in this way we identify the three things: either homogeneous, non-homogeneous, its order and its degree. Let us see an plus an minus 1 plus an minus 2 plus so on plus a1 plus a0. It is a particular recurrence relation. The first we considered, it's totally different from them. Rather it is n minus 1, n minus 2, but no, it's a reduced last term is a0. If there are such type of the recurrence relation, actually we call them homogeneous. We call them homogeneous, but we say order, they have no order. What's about degree? We say not defined. It is just like a sequence, not a recurrence relation. No, it has reduced to last term to 0. We define it has no order and no degree, but still it is homogeneous. see some particular examples. Say an is equal to sine of an minus 1 plus cos an minus 2. Simply, it is non-homogeneous. We say no order, no degree, because it contains the trigonometrical ratios. So we write it no order and no degree. It does not mean we cannot solve these problems. We can solve them with some other methods available in the mathematics, but here we are discussing about only the recurrence relation. So they do not belong to our topic, or they do not belong to this family. Why? They are not homogeneous, so they are no order and no degree. Then simply we can identify any recurrence relation into the homogeneous and non-homogeneous, and then to find their order and degree. Now we will start the solution for this. We will start with the homogeneous recurrence relations. How to solve the homogeneous recurrence relations? Remember, the problem with the solution is that every problem, or we can say every question, they follow the different theorems. If you will see in your booklets of the IGNOU, you will find the first topic, generating function. But generating function that can be understood only when we solve these homogeneous and non-homogeneous recurrence relation. Then we shall discuss about the generating function.